Welcome to the course Algorithmic Design. Let's move to these trees, okay? So that's the the last example I want to show, but there are multiple variations or multiple versions. So let's go back here. Aalto courses like design, tutorials, and then Christian grammars. Okay, so there's actually a couple, and let's see. Natural simple 2D tree. Okay, so let's open, for example, this simple 2D tree. Okay, so rather short code. Okay, so it's 38 lines. We can probably even sort of squeeze this because it's 2D. We can actually just go to the top. Okay, so to the top, and let's just, I think I can just run it. Iterations 10 should be okay. I just chose the branch angle is 90. That's, for example, 30. Okay, so this is like the most prototypical, the simplest standard example of sort of a tree that you can think of. And if you are interested in biology, you might notice that some of these regular branching structures, they look like less like trees as you know them, but they maybe resemble some of the kind of earlier kind of flora or species. I don't know what the types are in these types of ferns, for example. Let me just try to find help. Fern, plant. Okay, so it's actually called a fern. Okay, so ferns are these how do I call them? Old plants. they don't have seeds. They have spores, or so they're kind of again, I'm not a biologist, but there's like earlier versions of plants, and they're a bit disgusting because of the spores, but you can use them kind of at home and so on. They grow in forests in these kind of humid places, and if you look at them closely, you will see that they look a little bit again like trees, but they're very regular. Like they have a lot of regularity. So it's almost like these early plants just had they were more of this type. They had like a lot of regularity, and then as the plants evolved later, after millions of years, they started like just the way this algorithm or the principles, this subdivision worked or branching worked, just adapted and just became kind of different. Yeah, but this is like a simple example. And so in this code, I mean, it's very simple. There's just there's like a big loop here that kind of just runs. We have to start. So usually at the very beginning of subdivision or this branching, we have to always create the first element. Okay, so in shape grammars, this would be the first primitive. Okay, the first primitive from which we start. This is, I think, in shape grammars is using, this is called an axiom or axiom, something like that, axiom. And the reason is because we cannot create that shape by using any rule. Okay, so if I, for example, put here, I mean, I hope I'm not kind of over explaining this, but maybe iteration 0. Okay, so in shape grammars and these production systems, we have to start with some shape. Okay, and this is I think this is called axiom in this terminology. So it cannot be derived from any rules. This is just the shape that we start with. Okay, and in this case, it's just a line. Okay, and in iteration 2, or when we have put one iteration, that means one branching, we get it branches into 2. Okay, and then put 2, and then kind of continues and continues. Okay, I'll show you a lot of just here in this simplest example because it's kind of easy to see. There's a reduction factor, okay, 0.7. So that's the difference between the length of this line and every second branch. Also, when we branch, we are reducing the size of the branch. So reducing the length of the branch, and this is done by this factor. Okay, this we can also change. Okay, so if I kind of change this to, for example, 0.1, we are getting a very, very small branch. Okay, so this is obviously not realistic, but if you put it to 1, then there is no reduction. Okay, so so every branch is equally long, or that's also not realistic because branches usually do become smaller It's because the weight, you have more and more branches, you have this exponential growth, and then they have to be smaller because otherwise this branch, if it's equally thick as the other ones, it cannot carry that weight, obviously. So it's just when we scale, when there's more of them, they become shorter, but they also become thinner. Okay, that's why those branches that are on the top, they're kind of thinner and thinner. Okay, let me just put here branch reduction. Sorry. Delete. Okay, branch reduction 7. Okay, so I will not dwell too much on this example because it's kind of clear how it sort of works. Maybe here we can ramp up the iterations quite high because we are not working 3D, and we have only kind of 2 branches that come out. So what did I put now, 12 or 15? I forgot. Okay, so you can kind of go, you can go for sure. 15 is maybe too much. Okay, but you can see a little bit kind of how it works. Let's actually put it small into 7. And interesting things happen when you put, for example, branch angles that is 60 or 90 or 45. Okay, so suddenly you get these hexagons. Okay, and you can, if you set the reduction angle to something, then you can really start getting these regular shapes. Let me actually see what happens when I put 45. You can start creating these kind of patterns. Okay, 45 is maybe not that interesting, but which one? The one that I really like is 90, actually, because again, this is again branching. Okay, so it's that's one branch. Those are 2 branches. They branch in 90 degrees. Okay, so you get this kind of this is basically again very similar to this Sierpinski carpet, or there's a fractal looks like this, which I don't exactly know the name of, but one of these has looks exactly like this. Let's just ramp this up a little bit. Okay, so we would just kind of infinitely nest. Again, same rules. So this is also a tree. It just has a lot of regularity. Okay, but this almost looks like a parking lot or something. Okay, and in the lecture, you remember, I'll just go back quickly to the lecture because just quickly go back to the lecture. If you remember, recursion and grammars, just want to show you. So, it's not one of these, but there is for sure a fractal that looks exactly like this one here on the left. And yeah, this I want to show. So I hope you can kind of appreciate how kind of similar these 2 images are. Okay, so yeah, so this is the leaves of the veins of a leaf, and this is just this fractal here. Okay, let's actually continue. So this is a simple 2D tree. I have this natural 2D tree array. Okay, so we can extend this a little bit. So the same algorithm, but we just extend it a little bit and we create an array. Okay, we create a grid of trees and we add noise. Okay, so here all the parameters are the same. We have the same reduction angle or reduction factor. We have the same opening angle or branching angle. So that's why we get this super regularity. But in nature, of course, there's noise. So things are not always there. When they're replicated, they're not always replicated as exactly the same. There's some variation. And this we can simulate by basically adding some random noise. And here I call it jitter. So there's jitter angle and jitter reduction. So the angle will go there's some standard angle, and then we add and subtract 10. So 10 degrees. And then we do the same thing for reduction factor. So it can go from some 0.7, it can go then from 0.5 to 0.9. Okay, so that's also varying. But otherwise, everything is the same, except that we are also now creating like a grid of solutions. Okay, not just one solution, but a grid of solutions. And let me just do that. Okay, iterations 10, 3 grid size 5. Yeah, maybe that's okay. I just hopefully this will run. So when you work with computational design, like there was a thing comment from one of the students that, you know, what is actually the purpose? You know, one purpose is to use data or facilitate data. You take the data from the real world and you use that to inform your design. I didn't really show you examples of this, but that's one use case for sure. And the other one is to be able to create options or variations very quickly. Okay, so because you have a generator where you can create one generation or one sample, then you can use the same generator to create as many variations as you want. And then you're basically, you know, you lay them out on the grid exactly like this, and then you choose. Okay, so you're still sort of in control because you're controlling the parameters. They're random, but you know, these numbers are decided. Okay, so this jitter angle 10 and this 0.2, the jitter reduction, these are designed features. Okay, and even though you could say that here you don't really have control, but actually you do. I mean, you have a different level of control. And just to illustrate the point, I want to show you what happens. I take the same grid, okay, and now I want to, for example, increase this jitter angle. Let's put it to 60, and jitter reduction to maybe 0.6. Why not? Okay, let's try it again. Okay, so now I changed the boundary, or you know, you could say that you changed the boundary of the design space. Okay, all these trees, they have like a design space that they belong to. Okay, their parameters are bounded by some numbers, by some ranges, and you can change these ranges. Okay, select last. Okay, and obviously I got kind of a very, in this case, maybe a little bit extreme example. But again, the algorithm is the same. It's just that there's a lot more variation. Okay, actually, let's not be that extreme. Let's go one step further, one step. Then maybe we go 20, and jitter reduction, maybe we go 40. So we just kind of double it. Okay. Okay, so that is a little bit just to say that that, you know, even though it seems that you're not fully in control, you're still controlling the boundary conditions. Okay? And that's a little bit for you also to think about. If you're a designer, you know, how much control are you letting go, or how much control are you retaining in your design, and how much are you leading to this sort of variation, kind of, let's say, randomness. Okay, so this is now, we just kind of doubled the angle and we doubled the reduction, and we already got just bigger variation. Okay, we got something else. Okay, you can see here that as the reduction factor can vary quite a lot. Some branches end up very small, and some still end up very, very large. Okay, again, in nature, you see examples like this as well, or so you get asymmetrical trees. But you know, now you can kind of play a little bit. This probably not like this, but you know, this is maybe a little bit more realistic. Okay, so again, all of these are random, but you're just kind of controlling the boundary conditions of this randomness. You can also change here the tree grid size, so you can change to whatever number you want. And we'll not do that now, but basically you can kind of create, you know, 10 by 10, and then you have 100 samples. Now you can imagine that if you just want to use this as, you know, you want to put them in your plans. Again, you're a landscape architect. You just, you know, now you can take these are just lines in Rhino, and you can just put them in your plans if you want. Okay, so that's the 2D tree array, and the last one that I want to show you is the 3D version. File open. There's the 3D, and then there's the natural also 3D. Okay, so I'll show you both. Okay, this one is a bit longer. There's a lot more happening because we have to, everything that we did now in 2D, we have to do in 3D. Okay, so we have to really work with three-dimensional rotation. So we have to define these sort of rotation vectors. There's a little bit more happening here, but essentially it's a little bit the same structure. It's we also have a class here defined called class branch, and that is basically being sort of called. The parameters are here under main. Yeah, don't be confused. This was actually, again, written for another purpose. So this is usually how Python code is written. So you would put all your code in the main, a function called main, and then at the end you would call that function. So it's basically, you could just almost delete this and delete, you know, this, and then just indent this, all this backwards. It will work the same way, but this is actually a correct way of doing it. So all the code that you do in Python, or in general coding, it's usually good to just pack it into a function, you know, so that somebody can actually reuse your function. And it's just, then it's modularized. Also, if somebody loads it as now this file is 3D, you can load it as actually as a module. And if you just delete this line here, you can load it as a module, and this will not execute. All this will not execute until somebody calls this main function, for example. Okay, so it's just for the purpose of modularity and reusability of code, this is a little bit better. But again, just a kind of a technicality that doesn't need to concern you now. Okay, so here we change the parameters. So we have iteration 6, branch multiplier, opening angle, reduction. And yeah, let's actually start with iterations. Maybe let's try just 3 iterations and branch multiplier 3. So just run it. Okay. This is now from the top, but of course this is in 3D. Okay, so this is your tree. Okay, so we have a branch multiplier is 3. That means when we go out, when we branch, we branch into 3 directions, or into 3 other branches. And yeah, then you can just ramp up the iterations, and then you get something that looks like this. Okay, maybe reduction here is a bit too much. We put 7, 0.7. Okay. And when you look from the top, because again, you have this regularity, now you get this kind of triangle. So again, it's some type of a or in theory, it could be a type, it's basically a fractal, or but it's in 3D, so there's kind of overlap. Okay, you can actually also do this, what's the name, multi-pipe on this one. So let's just see what's the length of this one. Length 100 millimeters. So something like you know, multi-pipe, pipe radius 1. Let's see how that looks like. Okay, maybe let's do one more. Okay, so you can basically turn this into a geometry as well. Select lines, just delete them. Again, this is 3D printable. So if again, this is not really how trees look like, obviously, because rarely in the nature, I mean, trees don't really have this type of branching. Okay, this would be an exception to the rule. Again, there is a reason, I think, why nature decided to personify nature, why nature decided not to have these types of joints. I think they're not really efficient. So these ones would be sort of shifted, or that's explained in this book from Lindenmayer. But here we can just kind of approximately, we can use this. And again, I piped these, or used this multi-pipe, and you can see that, you know, the branches on the top are equally thick as the, you know, the ones below. And this is again something that is not realistic. So in nature, this cross section will go kind of down, down, down. Okay, but in theory, if you play a little bit now with modeling, you could get them, you know, to look basically like a little bit like real trees. Okay, and just to, let's change the branch multiplier. So let's put it, for example, 4. We get a different canopy. Okay, so if you look from the top, it is it looks like a square. Okay, and let's see if I put opening angle. What happens if I put 90? I really wonder, actually. Okay, so we get sort of a 3D version of, if you remember what we had before, like 3D version. So now just kind of coiling in on itself in 3D. Let's actually multiply this so we see it a little bit better. Yeah, everything is slower because the branch multiplier is higher, so there's like more elements. So we have the same number of iterations, 6, but there are more elements because every branch is branching to 4 other branches, not to 3. We could, of course, calculate very easily how many branches are there, and Rhino just has a limit to how many elements it can work with. Actually, now it's okay, didn't crash. Okay, so that's you can see that I think this multi-pipe subdivision doesn't work that well if you have like, if there's a lot of elements, then it gets a bit, I think, jaggedy, but otherwise it works quite well. Okay, and actually go back to here, opening angle 30. Let's actually just try one more, maybe branch multiplier 5, and just run this. Okay, and then from the top, because we have 5, this is a pentagon. Okay, so from the top, the canopy looks like a pentagon, and yeah, I mean, again, if you remember, if you know a little bit how kind of in the airport design, just see airport 3 pillars. Okay, so I just googled it quickly. This is used often, well, often in some airports use this to create these pillars that span very large spaces. For example, this guy, I guess, Stuttgart. Okay, so so you basically, again, and here the branching is actually exactly the same, or so it branches from one point. So you're kind of distributing the load of the roof onto smaller points, and they kind of go into sort of thicker and thicker elements until they kind of come down. I guess this also should Stuttgart, and maybe there's some other example somewhere else. Changi Airport, but it looks different. I guess these are all Stuttgart. Okay. Okay, so it is also used in architectural design, or so there is some sense behind this as well. Okay, and then again, if you have questions, you can ask. But the last example that I want to show you for today is the natural 3D. Okay, natural 3D, and the only difference here is that we add these jittering. So it's like noise. The code is actually exactly the same. You see, actually here we have 122, 122, and here we have 130. So we just had to add like 8 lines, to make this work. And there's this jittering happening here. There's probably somewhere at the beginning. No, you don't set the seeds. Yeah, this jittering is just being passed on here. And there's the opening angle and the reduction. There's like a random function. So Python random gives us a uniform random number between minus jitter parameter to plus jitter parameter. And this is just like a small amount that is added to the original opening angle and reduction factor. So you could think of it as, you know, the opening angle is still being used, but it has a certain deviation from this number that we defined here. Okay, and this gives us a bit more natural look. Actually, iterations maybe say to 6, and yeah, let's see. Okay, maybe actually go to 8. Okay, and then maybe with this code that we have this, maybe the closest we can get sort of to natural looking tree. Okay, it doesn't. It's still a little bit, you know, natural under under certain assumptions. So, you know, there are still things that are a little bit off. As I said, it's sort of where the branching exactly happens. But we are kind of deleting actually. It's kind of slow. We are slowly approaching this. You know, we could now play with the parameters, and we can sort of get it somewhere to the point.